Good morning or afternoon. My name is Makaita Maponga, and I used a random forest regression model to facilitate the rapid reconstruction of potential energy surfaces in an argon-oxygen system. Imagine you're a quantum chemist and you want to understand how two particles attract, repel, and ultimately collide. To do this, you need a perfect map of their interaction. In quantum chemistry, this map is called a potential energy surface. Think of it like a topographic map for a mountain range, but for molecules. It shows every valley of attraction and every peak of repulsion, defining the forces that govern everything from chemical reactions to the behavior of exotic matter. But here's the problem. Creating this map with the highest possible accuracy is incredibly difficult. The gold standard is a method called CCSDT, and at its heart, CCSDT is a way of solving the fundamental equations of quantum mechanics with exceptional precision. The problem is its staggering computational cost. CCSDT essentially tracks how every single electron in a system interacts with every other electron and then meticulously corrects for tiny, subtle correlations between them. It's like trying to predict the exact flow of a crowd by tracking every individual's movement and every social interaction simultaneously. This complexity means that for even a simple molecular system, a high-resolution map can keep a powerful supercomputer busy for weeks. This creates a fundamental bottleneck. It interesting things in physics, like Feshbach resonances, which are incredibly sharp quantum effects that act like precision tuning knobs for controlling how particles collide at near absolute zero temperatures. Understanding them could unlock new states of matter and revolutionize quantum simulation. So we're left with a critical question. Do we have to choose between accuracy and speed? Is the CCSDT gold standard also a cage that limits the pace of discovery? My research presents a solution. CCSDT is the ultimate cartographer. Can I train an apprentice? Can I teach a machine to read these perfect quantum maps so well that it can draw new ones with comparable accuracy, but in milliseconds instead of months? Over the next few minutes, I'll show you how I built and validated a machine learning pipeline that demonstrates that artificial intelligence can serve as a rapid, trustworthy surrogate for the most challenging quantum calculations, potentially opening new frontiers in quantum discovery. Faced with this challenge, my solution was to build a new kind of scientific tool, a machine learning pipeline that could learn the intricate patterns of quantum interactions and replicate them at incredible speed. The core concept here is what we call a surrogate model. Think of it this way. Instead of performing the exhausting month-long calculation every single time, you show an AI thousands of examples of already solved problems. You show it the input, the molecular configuration, and the perfect CCSDT output, the resulting energy. The AI learns the underlying mathematical relationship between them, so once it's trained and given a new configuration it's never seen, it can instantly predict the answer, bypassing the need for the prohibitively expensive calculation. To bring this concept to life, I engineered an automated computational pipeline. Let me walk you through its architecture. So first, I have the foundation, which is the data, and here is a sample of the input data. I used a high-fidelity data set of the argon-oxygen system calculated using the very CCSDT method I just discussed, and this provided the essential ground truth for my AI to learn from. And then this was the output data. And then next, the automated brain of the operation. I programmed a Python pipeline that begins with a function called read_excel_loose. Its job is to be a robust data ingestion tool. It intelligently scans the raw files, finds the headers, and cleans the data, ensuring a structured data set is produced, ready for analysis. This data is then passed to a function called detect_file_type. This is a classifier. It automatically analyzes the data and determines whether it's looking at cross-section data or a potential energy curve, routing it down the correct processing pathway. This automation was crucial for handling different data sets without manual intervention. The heart of the pipeline is the learning core for the potential energy data. The process potential curve function takes over. Here, I implemented and compared 3 distinct machine learning models to see which one was the best cartographer. The first one was a 4th-degree polynomial, which was the baseline. a simple, physically intuitive model. The second was a support vector regressor, which is a more complex model capable of capturing nonlinear patterns. And the last one was a random forest regressor. This one's an ensemble method. It doesn't rely on single prediction, but builds hundreds of decision trees and averages their results. Finally, the pipeline calls visualization functions that I coded to generate the publication quality figures you'll see in the results. In essence, I built a modular, self-contained system that takes raw quantum data as input and produces validated AI models and clear visualizations as output. This wasn't just pre-built tools. This was a from-the-ground-up engineering effort to create a new instrument for scientific discovery. So, did it work? The machine learning apprentice successfully learned the art of quantum cartography. The results not only confirmed my hypothesis, but exceeded expectations. This is the first result. The black dots represent the actual painstakingly calculated CCSDT data. The smooth red line is the prediction from the random forest model. As you can see, the agreement is not just good, it's visually perfect. The model has actually captured the entire topography of the interaction. The steep repulsive wall at short distances, the distinct potential well, and the molecule is most stable, and the long-range attractive tail. It has successfully learned the physics. In this one, we see the result for the excited state, this time using the polynomial model. While the fit is excellent, you can already see a key insight. The polynomial, being a simpler model, produces a smoother curve. This was the first clue that the random forest, with its ability to capture more complex, non-linear relationships, might be the best tool for this job. But in science, visual proof must be backed by hard numbers, so I need to quantify this performance. The table gives us the quantitative validation. The polynomial model achieved a respectable fit with a test set RMSE of 4.83 kilocalories per mole. This is good, but not great for precise work. An RMSE of 4.83 kilocalories per mole is good because it successfully demonstrates that the model has learned the fundamental shape and trends of the potential energy surface. It's not guessing randomly. It has captured the correct physics at a macroscopic level. This level of accuracy might be sufficient for very rough initial screening of molecular behavior or for educational purposes, where seeing the general trend is the goal. However, it's not great for precise work because of the energy scales involved in chemical processes. To put that number in context, a chemical bond strength, a typical chemical bond has a strength of approximately 100 kilocalories per mole, and an error of 5 kilocalories per mole represents a 5% error in calculating something as fundamental as the energy required to break a bond. This is too large for a reliable prediction, and the rate of a chemical reaction depends exponentially on the energy barrier via the Arrhenius equation. So an error of just 1 to 2 kilocalories per mole can change a predicted reaction rate by a factor of 5 to 10. An error of approximately 5 kilocalories per mole makes the prediction rate wrong by orders of magnitude, rendering it useless for designing a chemical synthesis or understanding kinetic processes. The affinity of a drug molecule for its protein target, or the binding energy in a molecular complex, is often determined by interactions worth only 1 to 3 kilocalories per mole. So an error of 4.83 kilocalories per mole would completely swamp the signal, making it impossible to distinguish a strong binder from a weak one. To accurately predict vibrational frequencies in spectroscopy, you need an error well below 1 kilocalorie per mole, and an error of 4.83 kilocalories per mole would lead to predicted frequencies that are wildly incorrect. So think of it like forecasting the weather. A model that correctly predicts that it'll be warmer in summer than in winter is good. It has the right general trend, but a model that needs to tell a farmer the exact overnight low to prevent frost damage must be great. It needs precision down to a single degree. The polynomial model gives us a seasonal trend. The random forest model gives us a precise frost warning. So in short, the 4.83 kilocalorie per mole error from the polynomial model shows it understands the season of the molecular interaction, but it lacks the precision needed for the delicate frost warnings of quantum chemistry. The random forest model's error of 1.47 kilocalories per mole enters the realm of chemical accuracy, where its predictions become reliable enough to guide real experimental and theoretical work. The SVR model, surprisingly, failed to learn the pattern effectively with a very low R squared and a high RMSE of 6.31 kilocalories per mole. And now, if you look at the random forest model, it achieved a near perfect R squared training score, and most importantly, an R squared test score of 0.947, which means it explains 94.7% of the variance in the data it has never seen before, so it generalized brilliantly. And then the most critical number here is the RMSE, 1.47 kilocalories per mole. The goal was to achieve what's known as chemical accuracy, which is typically an error of less than 1 to 2 kilocalories per mole. And it didn't just meet the goal, it surpassed it. This result is not a statistical abstraction. It means the model's predictions are trustworthy enough to guide real scientific experiments. And finally, a rigorous model requires a rigorous error analysis. This plot shows the residual errors across all distances. What you want to see is what I have here, a random cloud of points centered around 0. There's no bias curves or trends, and this tells us the model has no systematic bias. It is equally accurate across the entire landscape, from the repulsive wall to the tail. This is the most intuitive validation. Here, I plot the model's prediction against the true values. The red dashed line is the line of perfect agreement, and as you can see, the data points form a tight cluster right on top of that line. This is the ultimate visual confirmation that the surrogate model isn't just working, it's producing highly accurate and reliable results. In summary, the results provide a three-part confirmation. Visually, the curves are identical. Quantitatively, the accuracy meets a chemical standard, and statistically, the errors are minimal and unbiased. The random forest model has proven itself as a highly effective surrogate for quantum chemical calculations. Next, for the bigger picture and future vision. Validating a model is one thing, but understanding its impact is another. So, what does a tool like this actually enable? The implications extend beyond a single successful prediction and point towards a shift in how we can do science. The most immediate benefit is what is called democratization. Right now, the ability to run high-fidelity quantum simulations is gated by access to massive supercomputing clusters, which are resources typically available only to well-funded research institutions at elite universities. My model, which runs on a standard laptop in milliseconds, shatters that barrier. It puts a powerful quantum simulation tool into the hands of an undergraduate at a small college, a researcher in a developing nation, or a curious high school student. So we're no longer just democratizing data, we're democratizing discovery itself. And this leads directly to the second benefit, radical acceleration. So imagine the traditional process. A theorist has a new idea, submits a job to a computing queue, and waits weeks for the results, only to find it was a dead end. This is a slow, iterative loop. Now, replace that with a process where they can test thousands of variations on that idea in a single afternoon. This isn't just a slight speed up, it enables a completely new, high throughput model of scientific exploration. Researchers can scan vast parameter spaces to locate the most promising candidates for real-world experiments, turning the slow process of discovery into a rapid process of guided search. The PES generator I've built is a monumental step, but it's just the first module in a larger pipeline. The complete scientific killer system can I predict its scattering behavior and locate quantum resonances like Feshbach resonances. We solved the first part, and so the next logical step is to build the module that answers the second part. This is where the graph neural network I've designed comes in. A graph neural network is perfectly suited to take the PES because it inherently understands the structure of molecules. Atoms are natural nodes and chemical bonds are edges, allowing the graph neural network to process molecular geometry directly. This architecture automatically respects crucial physical symmetries, so it doesn't matter if we rotate the molecule, the GNN will recognize it as the same system, and this structural intelligence enables the GNN to learn the direct complex mapping from the molecular geometry defined by the PES to the resulting quantum collision cross-sections and resonance features, effectively learning the dynamic scattering behavior implied by the static energy landscape. This capability far surpasses conventional neural networks which struggle with such geometrically structured data. Completing this would create a true end-to-end predictive pipeline, and a scientist could input a basic molecular description and in moments receive a precise prediction of a scattering behavior, bypassing months of sequential computational work. For this vision to be fully realized, the broader scientific community must engage. The next few steps involve other computational scientists applying this pipeline to a diverse range of molecular systems to stress test its generalizability, and theorists and experimentalists adopting this tool, integrating its rapid predictions into their workflow to decide which real-world experiments are the most promising. This work does more than just present a successful model, it provides a foundational component for a new, accelerated approach to scientific discovery, one that is more accessible, more efficient, and ultimately more powerful. I asked a simple question, could machine, and the answer, as demonstrated by the results, is a resounding yes. I successfully developed and validated a machine learning surrogate that can reconstruct potential energy surfaces with chemical accuracy, achieving an RMSE of just 1.47 kilocalories per mole. This isn't just a statistical result, it's a functional one. It means I've created a new, reliable scientific instrument. This instrument is fast, turning weeks of computation into milliseconds. It is accessible, running on hardware available to almost everyone, and it is accurate, producing results trustworthy enough to guide real scientific inquiry. But more than that, this work is a proof of concept for a new paradigm. It shows that AI can be more than just a pattern finder. It can be a powerful collaborator in fundamental science, helping us navigate the complex quantum world with unprecedented speed. I have built the first crucial model, and now the path forward is clear to integrate this with a graph neural network, completing the end-to-end pipeline to directly predict quantum phenomena and accelerate the discovery of new physics. Thank you.